In this video, we're going to discuss the instantaneous rate of change and how it applies to what we're going to be doing, which is known as the derivative. We're already familiar with average rate of change, which is just a slope between 2 points. So let's say I want to find the average rate of change between x equals 1 and x equals 4. All I have to do is identify the 2 points on this function. This function, by the way, is written right here, and I'm going to be using it fairly regularly throughout this video to illustrate the points. So all we have to do in order to find the average rate of change is find the slope of that line, and that will tell me, on average, how much the function value changes for every change in x that occurs on this interval. So all I have to do is substitute in 5 minus 2, 4 minus 1. We get 3 over 3, and that's 1. That's, again, fairly straightforward. We go up 1 and over 1, up 1 and over 1. And that's clear, and that's very easily defined. And we could have gotten our values of y by simply substituting in f of 1 and f of 4 to get the 2 and the 5, respectively. What we're going to be more interested in calculus is finding the instantaneous rate of change. In other words, what is the slope at one point, or the slope of the tangent line to the curve? So instantaneous rate of change is the slope of the line tangent to the curve. So let's say I don't really want to know what the function changes on average from 1 to 4. Let's say I want to know exactly at 3 what is the change in the function value at that exact point for a slight change in x. So here we obviously can't apply the slope formula because we only have one point, that's 3, 2. So let's examine how we're going to find such a slope when we only have one point. Let's draw a generic function. It looks something like this. It doesn't matter what we use. I use this graph because I think it's the easiest to illustrate that point. And let's say I want to know the instantaneous rate of change, that is the slope of the tangent line at this x value. I'm going to call this here f of x. And I want to know the slope of this tangent line. So what I'm going to do is, I'm obviously not able to take the slope of that line because I only have one point. So what we're going to do is we're going to create a second point here somewhere. I'm going to say that this is x plus h. You can call it whatever you want, but the generally accepted convention is to use x plus h, therefore defining that space there as h, because we've added h in order to create the second point. So then this is f of x plus h. So let's create this average rate of change slope, and we can draw a line between these 2 points and calculate the average rate of change. So the average rate of change is going to be y2, which is f of x plus h, minus y1, which is f of x, all over x plus h, that's x2, minus x1, which is just x. So we can simplify this formula down to f of x plus h minus f of x all over h. And again, this is just a really simple slope formula, no calculus involved just yet. But we can see that this slope, although it is an okay estimation of this green slope, is not a very good slope estimation. So we want to make it better. Well, how can we make it better? One way we can make it better is by making the h smaller. So if I now make the second point here, this slope is a lot closer to the green slope that we want, but not quite there, but definitely better. And if I make it even closer, let's say I draw it here, that second point, then we're getting really close to that green slope. So as I make h smaller, the slope of the average line, the average rate of change, gets much closer to the slope of the tangent line. Now, and you can pause the video if you want to think about this before answering the question, what would h have to be, theoretically, in order to get the exact slope value at that point? And the answer to that is 0. If h equals 0, then the m average is going to exactly equal the m of the tangent. However, if the h is 0, then f of x plus h equals f of x, and our entire slope reduces to 0 over 0. If we substitute in f of x up here rather, and then an h of 0 here, we get 0 over 0, and obviously that tells us nothing. So how do we solve this problem? Well, several units back, we explored something called a limit, which allows us to determine the value of a function that is otherwise indeterminate, 0 over 0. So let's examine what we could do with this. We can't make h 0, but we could certainly take the limit as h approaches 0. If h approaches 0, then at that exact point, the m average will approach the m tangent. If we apply that to our existing formula up here, then we can conclude that the m of the tangent line is exactly equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is a really, really, really important formula that we're going to be using quite a bit to allow us to calculate the instantaneous rate of change. So this is one you need to be able to commit to memory and apply. So let's talk about the application of this formula. I'm going to copy it over to the next page here, and we're going to use the function that we talked about at the beginning of this video. So again, remember, the m of the tangent line, or we will call it the f prime of x, is equivalent to f of x plus h minus f of x all over h. Let's apply that here. The first thing I'm going to do is get the f of x plus h. So f of x plus h, from basic function theory, I replace all the x's with x plus h. So this is x plus h times x plus h minus 4x minus 4h plus 5. And upon foiling this out, we've got x squared plus 2xh plus h squared minus 4x minus 4h plus 5. So that's what we're going to end up substituting into the f of x plus h component of our newfound slope formula. We already know the f of x. That's easy. That's here. And h is just an arbitrary value that we're going to take the limit of to begin with. Excuse me, I didn't copy the complete formula here. This is going to be the limit as h approaches 0 of all of this. So what we're going to do is we're going to substitute this value in, leaving the h's as they are. So I'm going to say that the f prime of x is equivalent to the limit as h approaches 0 of x squared plus 2xh plus h squared minus 4x minus 4h plus 5 minus f of x, which is x squared minus 4x plus 5, all over h. And again, I'm just going to distribute that negative here, so we're going to get the limit as h approaches 0 of x squared plus 2xh plus h squared minus 4x minus 4h plus 5 minus x squared plus 4x minus 5 all over h. Now let's simplify the top. X squared minus x squared is 0. Negative 4x plus 4x is also 0. And it doesn't look like we can simplify anything else, so I'm going to rewrite that simplified version here. So we've got the limit as h approaches 0 of 2xh plus h squared minus 4h. Looks like we've got a plus 5 and a minus 5 here that'll also add to 0. And all of that over h. Now, we're going to talk about why we've been able to eliminate all of these terms in a moment, but you should now recognize that I can factor an h out of the top and be left with 2x plus h minus 4 all over h. And now the h's, which we were previously unable to substitute in because we'd get a 0 in the denominator, reduce out to 1. And we're left with the limit as h approaches 0 of 2x plus h minus 4. Now we can go ahead and substitute our 0 as we have done in limit theory before, and we're left with 2x minus 4. So f prime of x, that is the slope of the tangent line, at any given point on this graph is equivalent to 2x minus 4. This is a fairly lengthy process the first couple of times around. We're going to learn some rules that will make finding the derivative a little bit easier. But now, for now, this is the general method, and this will work for any function as long as you can correctly algebraically manipulate it. The objective, remember, if we sub in the h of 0 here, all of these terms will go to 0, and then we're going to subtract out all the other terms, and we're going to end up with 0 over 0 again. So substituting in and distributing everything out allows us to get rid of the h's. This is a really, really, really important step right here, because otherwise we're just going to end up with 0 over 0 no matter what we do. That being said, if you're at this stage right here, and you have a term in the numerator that does not have an h in it, that is, you're unable to factor out an h from the entire numerator, then you've got a mistake earlier on, probably somewhere around here. So let's take this work now, and let's use it as an example over here. So remember, we found that the derivative function is 2x minus 4. So that is the slope at any point, the slope of the tangent line is equivalent to 2 times the x value of that point minus 4. Well, let's go back to the beginning here where we tried to find the approximate slope at x equals 3. So if I sketch the line that's tangent to it, it's not perfect, but we can see that we are pretty close to this point here. So we could probably assume in this case that this point is at least close to what we're looking for. And let's take the slope of that line. Well, we've got 4 minus 2 over 4 minus 3, which is 2 over 1, which is 2. Okay, so that's 2. That means the slope of that tangent line should be 2. Well, let's see. If I substitute in the 3, I'm going to get 2 times 3 minus 4, which is, of course, 6 minus 4, or 2. So our graph seems to agree that we found our derivative correctly, and we can find the slope of the tangent line. Of course, if I substitute in a different value, let's say I want the instantaneous rate of change at 2. Now, if we draw that tangent line, you should all be able to tell me that the slope of this is 0. Well, let's verify that to be true. Let's take the f prime of 2, and that would be 2 times 2 minus 4, which, of course, is 0. We're going to go a little bit more in depth on this at a later date, as well as identify easier ways to find the derivative than to have to go through the algebraic definition every single time. But it is a formula you need to know, and you need to understand the premise of how to apply the limit theory to finding this formula. Thank you for watching.